Hello everyone, my name is Pujita and today I'm going to explain about the topic called vector random variables and joint distribution. What do you mean by a vector random variable? A vector random variable is a collection of multiple random variables considered together as a single entity. Rather than analyzing outcomes one at a time, we capture the complete multidimensional picture simultaneously. Mathematical notation: x equals to x1, x2, and so on xn. Here, each xn is a random variable. Real world example is to check height, weight measured jointly on a single person. Multidimensional outcomes. Model complex phenomena with multiple dimensions. What do you mean by joint distribution function? The joint cumulative distribution function quantifies the probability that all random variables simultaneously fall below specified thresholds. It represents the complete probabilistic behavior of the entire system. Two variable cases: f of x comma y comma small x comma y equals to p of x less than or equals to small x comma y less than or equals to small y. The probability that x does not exceed x and y does not exceed y simultaneously. General form is fx of x1 comma x2 comma and so on xn equals to p of x1 less than x1 comma and so on xn less than xn. Extends to any number of random variables. What do you mean by joint probability mass and density functions? A joint PMF Px, y of xy gives the probability that discrete random variables x and y both take on specific values simultaneously. To be a valid PMF, all probabilities must be non-negative and the sum overall possible pairs must equal 1. The joint PMF fully describes the probabilistic behavior of the random vector x, y for discrete distributions. For example, for two paired dice, the probability of rolling specific pairs such as 2, 5 is 1 by 36 and there are 36 possible pairs, each equally likely. The marginal PMF for x can be obtained by summing over all possible values of the other variables. Independence: x and y are independent if px, y of xy equals to px of x into py of y for all x, y. The joint PMF makes it possible to compute conditional probabilities such as the probability that x equals to x, that can be given as p of x equals to x by y of y equals to p of x comma y of xy by py of y. Joint probability density function. The joint PDF describes the probability density at each point for continuous random variables x and y. Unlike the PMF, the joint PDF values can be greater than 1, but probabilities for actual regions are found by integrating the PDF over those regions. Properties of joint distribution functions. Properties of joint distribution function are essential for understanding multivariate probability models and ensuring mathematical consistency. Main properties are: non-decreasing property. The joint cumulative distribution function, that is CDF, increases or stays constant as any of its arguments increases. It is never decreasing in any variable. Next, boundary conditions. The function satisfies certain limits, that is, f of minus infinity comma y equals to f of x comma minus infinity equals to 0 and f of infinity comma infinity equals to 1. Increasing any argument far enough yields the total probability 1. Pushing any arguments to minus infinity yields 0. Next, probability extraction. The joint CDF allows the recovery of probabilities for specific regions or events. Marginal distribution function. Marginal distribution functions allows us to understand the behavior of individual random variables within a multivariate system by removing the effects of the other variables. Extracting marginal distributions. Marginal distributions provide the probability distribution of a single variable regardless of the values taken by the others, revealing its unique behavior within the joint system. Discrete case. The marginal probability mass function for a variable x is found by summing the input PMF over all possible values of y. That is, Px of x equals to summation y Px comma y of xy. This operation collapses the joint distribution along one dimension, leaving the distribution for x alone. Continuous case. The marginal probability density function for x comes from the integrating the joint PDF over all possible values of y. That is, fx of x equals to integral minus infinity to infinity f of x comma y of x comma y dy. This process removes the influence of y, isolating x probability density. Marginal distribution serves as the signature of each variable, showing how it behaves on its own even though it may be part of complex systems. It is useful for analyzing sections of large systems, focusing on variables of interest without needing the full joint behavior. Marginal distributions are fundamental tools in probability, statistics, and data science for reducing complexity and extracting actionable insights about specific variables within multivariate environments. Next, conditional distribution and density functions. Conditional distributions reveal how one variable behaves when another is fixed to a specific value. They are essential for understanding dependence relationships and updating beliefs based on new information. For discrete case, p of x by y equals to p of x comma y by py of y. Probability of x given y that equals to y, conditional on y being observed. For continuous case, f of x by y equals to f of x comma y by fy of y. It reveals independent variables have p of x by y. Let us take an example, that is campus job selection. 2 juniors and 3 seniors apply for the 2 positions selected randomly. Here, this example illustrates about joint, marginal, and conditional distributions in a concrete setting. First, here the possible outcomes comes in 3 cases, that is 0 juniors, 2 seniors, or 1 junior, 1 senior, or either 2 juniors or 0 seniors. Here the joint probabilities are for P of 0, 2 is 3 by 10, P of 1, 1 is 6 by 10, and P of 2, 0 is 1 by 10. Here the marginals are, if for P of x equals to 0, it is 3 by 10. For P of x equals to 1, it is 6 by 10. And for P of x equals to 2, that is 1 by 10. Here same as for seniors, P of y equals to 2, that is 3 by 10, P of y equals to 1, that is 6 by 10, and P of y equals to 0, that is 1 by 10. Visualizing joint and marginal distributions is key for developing institution about how random variables behave individually and together. This visualization help reveal dependencies like in independent cases, the distribution is separable. The plot factors into the product of marginals. In dependent cases, the plot may show peaks or valleys corresponding to the correlated outcomes. Visualization representations make abstract probability concepts concrete, helping identify relationships, independences, or clustering in data, critical for statistical interference and real world applications. These approaches are widely used in statistics, data science, machine learning for understanding model structure and guiding decision making. The summary of this concept is joint distributions and their properties forms the mathematical foundation for modern statistics and data science applications. These are helped in model complexity like vector random variables capture multidimensional phenomena accurately. Joint distribution reveal complete independences among variables. Marginal and conditional distributions enable investigation of on specific aspects, and here they are essential for multivariate statistics, machine learning, and data science. They are used in real world applications. Thank you.